Welcome back to the DevOps Week by Simplilearn. So far, we have mastered DevOps testing. The next crucial stage in DevOps Week is the integration of DevOps with cloud. The benefits of using DevOps with cloud projects are also becoming better defined. They include application development, speed to delivery to meet the needs of the business units faster, user demands that quickly fold back into the software, and low cost for development, testing, deployment, and operations. In today's session, we'll be learning exactly how to integrate DevOps with cloud and experience the real-time working of DevOps with popular cloud platforms. So without further ado, let's get started.
So we will start by watching a short animated video to understand the basics of DevOps and then learn the life cycle of DevOps followed by its advantages. We will look at what cloud computing is, the benefits of cloud computing, and the different cloud providers. Moving ahead, we will learn the important DevOps tools and frameworks such as Git, Jenkins, Maven, Selenium, Docker, and others. Then, we will focus on learning about the different cloud providers and explore more about them. So we will learn about Amazon Web Services, Microsoft Azure, and Google Cloud Platform in detail with hands-on demonstrations. So let's get started.
Meet Tim. Tim builds a robot in his lab, a climate-controlled and pollution-free environment. Once he's done, he drops the robot off at his project partner, Mia's house. Mia takes it out to her backyard to ensure that the robot meets the requirements. But here is where the problem arises. The change in the environment causes the robot to malfunction. Mia is now really annoyed and she has a lot to correct. And it seems to her as though Tim didn't really do much. This wall between them leaves the poor robot to bite the dust. Well, what if we broke this wall? Tim and Mia now work together in a common space. Tim develops each block of functionality of the robot, which is then immediately checked by Mia. Both are now working simultaneously instead of waiting on the other to finish their task. As and when a feature is ready for use, they are put together to build the final product. They develop a common mindset and share ideas. To further speed up the process, they use several tools which can automate every stage. This means that the robot is now ready sooner with less iterations and manual work. From an organization perspective, Tim would be the developer while Mia the operations. Their union is the core of the DevOps approach. DevOps has several stages and set of tools to automate each of these stages. Let's have a look at these. Tim first puts down a plan. In terms of software, this could mean deciding on the modules and the algorithms to use. Once he has the plan, he now codes the plan. With tools such as Git, Tim has a repository for storing all the codes and their different versions. This is called version control. Next, this code is fetched and made executable. This is the build stage. Tools such as Gradle and Maven will sort this out. Now before deployment, the product is tested to catch any bugs. The most popular tool automating testing is Selenium. Once the products are tested, Mia must deploy it. The deployed product is then continuously configured to the desired state. Ansible, Puppet, and Docker are some of the most common tools used that automate these stages. Now, every product is continuously monitored in its working environment. Nagios is one such tool that automates this phase, and the feedback is fed back to the planning stage. And finally, we have the core of the DevOps lifecycle, the integration stage. Tools such as Jenkins is responsible for sending the code for build and test. If the code passes the tests, it's further sent for deployment. This is called continuous integration. Let's now have a look at an organization that has adopted the DevOps approach. Which of the below sequence of steps would they follow to develop a software? Leave your answers in the comment section. Keep an eye out for the right answer on the comment section or our YouTube community. Giants such as Amazon, Netflix, Target, Etsy, and Walmart have all adopted DevOps and seen a considerable increase in delivery and quality. In 2014, an hour of downtime for Netflix would cost it $200,000. it became absolutely crucial that Netflix prepared themselves for any sort of failure. And so, they took to the DevOps approach and implemented it in the most unique way. They developed a tool called the Simian Army. This tool created failures and automatically deployed them in an environment that did not affect the users. The team would troubleshoot these failures, and this gave them enough experience to deal with any degree of collapse. With everything being automated and happening simultaneously, organizations can now deliver at a much faster pace. So, considering the benefits of DevOps and its divergence from the traditional methods, would DevOps be the future? Let us know what you think in the comment section below.
Hello, this is Matthew with Simply Learn, and today we're going to introduce you to DevOps. So let's go through Waterfall. So Waterfall is a traditional delivery model that's been used for many decades for delivering solutions, not just IT solutions and digital solutions, but even way before that. It has its history that goes back to World War II. So Waterfall is a model that is used to capture requirements and then cascade each key deliverable through a series of different stage gates that is used for building out the solution. So let's take you through each of those stage gates. The first that you may have done is requirements analysis. And this is where you sit down with the actual client and you understand specifically what they actually do and what they're looking for in the software that you're going to build. And then from that requirements analysis, you'll build out a project plan so you have an understanding of what the level of work is needed to be able to be successful in delivering the solution. After that, you've got your plan, then you start doing the development, and that means that the programmers start coding out their solution. They build out their applications, they build out the websites, and this can take weeks or even months to actually do all the work. When you've done your coding and development, then you send it to another group that does testing, and they'll do full regression testing of your application against the systems and databases that integrate with your application. You'll test it against the actual code, you'll do manual testing, you do UI testing. And then after you've delivered the solution, you go into maintenance mode, which is just kind of making sure that the application keeps working. If there's any security risks, that you address those security risks. The problem you have, though, is that there are some challenges, however, that you have with the waterfall model. The cascading deliveries and those complete and separated stage gates means that it's very difficult for any new requirements from the client to be integrated into the project. So if a client comes back and the project has been running for 6 months and they've gone, hey, we need to change something, that means that we have to almost restart the whole project. It's very expensive and it's very time consuming. Also, if you spend weeks and months away from your client and you deliver a solution that they are only just going to see after you spend a lot of time working on it, they could be pointing out things that are in the actual final application that they don't want or are not implemented correctly or lead to just general unhappiness. The challenge you then have is if you want to add back in the client's feedback to restart the whole waterfall cycle again. So the client will come back to you with a list of changes, and then you go back and you have to start your programming, and you have to then start your testing process again, and just you're really adding in lots of additional time into the project. So using the waterfall model, companies have soon come to realize that the clients just aren't able to get their feedback in quickly, effectively. It's very expensive to make changes once the teams have started working. And the requirement in today's digital world is that solutions simply must be delivered faster. And this has led for a specific change in Agile. And we start implementing the Agile model. So the Agile model allows programmers to create prototypes and get those prototypes to the client with the requirements faster. And the client is able to then send the requirements back to the programmer with feedback. This allows us to create what we call a feedback loop, where we're able to get information to the client and the client can get back to the development team much faster. Typically, when we're actually going through this process, we're looking at the engagement cycle being about 2 weeks. And so it's much faster than the traditional waterfall approach. And so we can look at each feedback loop as comprising of 4 key elements. We have the planning, where we actually sit down with the client and understand what they're looking for. We then have coding and testing, that is building out the code and the solution that is needed for the client. And then we review with the client the changes that have happened. But we do all of this in a much tighter cycle that we call a sprint. And that typically a sprint will last for about 2 weeks. Some companies run sprints every week, some run every 4 weeks. It's up to you as a team to decide how long you want to actually run a sprint. But typically it's 2 weeks. And so every 2 weeks, the client is able to provide feedback into that loop. And so you were able to move quickly through iterations. And so if we get to the end of sprint 2 and the client says, hey, you know what, we need to make a change, you can make those changes quickly and effectively for sprint 3. What we have here is a breakdown of the ceremonies and the approach that you bring to Agile. So typically what will happen is that a product leader will build out a backlog of products, and what we call a product backlog. And this will be just a whole bunch of different features, and they may be small features or bug fixes, all the way up to large features that may actually span over multiple sprints. But when you go through the sprint planning, you want to actually break out the work that you're doing so the team has a mixture of small, medium, and large solutions that they can actually implement successfully into their sprint plan. And then once you actually start running your sprint, again, it's a 2-week activity. You meet every single day with the actual sprint team to ensure that everybody is staying on track, and if there's any blockers, that those blockers are being addressed effectively and immediately. The goal at the end of the 2 weeks is to have a deliverable product that you can put in front of the customer, and the customer can then do a review. The key advantages you have of running a sprint with Agile is that the client requirements are better understood because the client is really integrated into the Scrum team. They're there all the time. And the product is delivered much faster than with a traditional waterfall model. You're delivering features at the end of each sprint versus waiting weeks, months, or in some cases years for a waterfall project to be completed. However, there are also some distinct disadvantages. The product itself really doesn't get tested in a production environment. It's only being tested on the developer computers. And it's really hard when you're actually running Agile for the sprint team to actually build out a solution easily and effectively on their computers to mimic the production environment. And the developers and the operations team are running in separate silos. So you have your development team running their sprint and actually working to build out the features. But then when they're done at the end of their sprint and they want to do a release, they kind of fling it over the wall at the operations team. And then it's the operations team job to actually install the software and make sure that the environment is running in a stable fashion. That is really difficult to do when you have the two teams really not working together. So here we have is a breakdown of that process with the developers submitting their work to the operations team for deployment. And then the operations team may submit their work to the production servers. But what if there is an error? What if there was a setup configuration error with the developer's test environment that doesn't match the production environment? There may be a dependency that isn't there. There may be a link to an API that doesn't exist in production. And so you have these challenges that the operations team are constantly faced with. And their challenge is that they don't know how the code works. So this is where DevOps really comes in. And let's dig into how DevOps, which is developers and operators working together, is the key for successful continuous delivery. So DevOps is an evolution of the Agile model. The Agile model really is great for gathering requirements and for developing and testing out your solutions. And what we want to be able to do is kind of address that challenge and that gap between the ops team and the dev team. And so with DevOps, what we're doing is bringing together the operations team and the development team into a single team. And they are able to then work more seamlessly together because they are integrated to be able to build out solutions that are being tested in a production-like environment so that when we actually deploy, we know that the code itself will work. The operations team is then able to focus on what they're really good at, which is analyzing the production environment and being able to provide feedback to the developers on what is being successful. So we're able to make adjustments in our code that is based on data. So let's step through the different phases of a DevOps team. So typically you'll see that the DevOps team will actually have 8 phases. Now this is somewhat similar to Agile, and what I'd like to point out at the time is that again, Agile and DevOps are very closely related, that Agile and DevOps are closely related delivery models that you can use. With DevOps, it's really just extending that model with the key phases that we have here. So let's step through each of these key phases. So the first phase is planning, and this is where we actually sit down with a business team and we go through and understand what their goals are. The second stage is, as you can imagine, and this is where it's all very similar to Agile, is that the coders actually start coding. But they'll start using tools such as Git, which is a distributed version control software. It makes it easier for developers to all be working on the same code base rather than bits of the code rather than them working on bits of the code that they are responsible for. So the goal with using tools such as Git is that each developer always has the current and latest version of the code. You then use tools such as Maven and Gradle as a way to consistently build out your environment. And then we also use tools to actually automate our testing. Now, what's interesting is when we use tools like Selenium and JUnit, is that we're moving into a world where our testing is scripted, the same as our build environment and the same as using our Git environment. We can start scripting out these environments. And so we actually have scripted production environments that we're moving towards. Jenkins is the integration phase that we use for our tools. And another pointer here is that the tools that we're listing here, these are all open source tools. These are tools that any team can start using. We want to have tools that control and manage the deployment of code into the production environments. And then finally, tools such as Ansible and Chef will actually operate and manage those production environments so that when code comes to them, that code is compliant with the production environment, so that when the code is then deployed to the many different production servers, that the expected results of those servers, which is you want them to continue running, is received. And then finally, you monitor the entire environment so you can actually zero in on spikes and issues that are relevant to either the code or changing consumer habits on the site.
Imagine you're the owner of a small software development firm and you want to scale your business up. However, a small team size, the unpredictability of demand, and limited resources are roadblocks for this expansion. That's when you hear about cloud computing. But before investing money into it, you decide to draw up the differences between on-premise and cloud-based computing to make a better decision. When it comes to scalability, you pay more for an on-premise setup and get lesser options too. Once you've scaled up, it is difficult to scale down and often leads to heavy losses in terms of infrastructure and maintenance costs. Cloud computing, on the other hand, allows you to pay only for how much you use, with much easier and faster provisions for scaling up or down. Next, let's talk about server storage. On-premise systems need a lot of space for their servers, notwithstanding the power and maintenance hassles that come with them. On the other hand, cloud computing solutions are offered by cloud service providers who manage and maintain the servers, saving you both money and space. Then we have data security. On-premise systems offer less data security, thanks to a complicated combination of physical and traditional IT security measures, whereas cloud computing systems offer much better security and lets you avoid having to constantly monitor and manage security protocols. In the event that a data loss does occur, the chance for data recovery with on-premise setups are very small. In contrast, cloud computing systems have robust disaster recovery measures in place to ensure faster and easier data recovery. Finally, we have maintenance. On-premises systems also require additional teams for hardware and software maintenance, loading up the costs by a considerable degree. Cloud computing systems, on the other hand, are maintained by the cloud service providers, reducing your costs and resource allocation substantially. So now, thinking that cloud computing is a better option, you decide to take a closer look at what exactly cloud computing is. Cloud computing refers to the delivery of on-demand computing services over the internet on a pay-as-you-go basis. In simpler words, rather than managing files and services on a local storage device, you'll be doing the same over the internet in a cost-efficient manner. Cloud computing has two types of models: deployment model and service model. There are three types of deployment models: public, private, and hybrid cloud. Imagine you're traveling to work. You've got three options to choose from. One, you have buses, which represent public clouds. In this case, the cloud infrastructure is available to the public over the internet. These are owned by cloud service providers. Two, then you have the option of using your own car. This represents the private cloud. With the private cloud, the cloud infrastructure is exclusively operated by a single organization. This can be managed by the organization or a third party. And finally, you have the option to hail a cab. This represents the hybrid cloud. A hybrid cloud is a combination of the functionalities of both public and private clouds. Next, let's have a look at the service models. There are three major service models available: IaaS, PaaS, and SaaS. Compared to on-premise models, where you'll need to manage and maintain every component, including applications, data, virtualization, and middleware, cloud computing service models are hassle-free. IaaS refers to infrastructure as a service. It is a cloud service model where users get access to basic computing infrastructure. They are commonly used by IT administrators. If your organization requires resources like storage or virtual machines, IaaS is the model for you. You'll only have to manage the data, runtime, middleware, applications, and the OS, while the rest is handled by the cloud providers. Next, we have PaaS. PaaS, or Platform as a Service, provides cloud platforms and runtime environments for developing, testing, and managing applications. This service model enables users to deploy applications without the need to acquire, manage, and maintain the related architecture. If your organization is in need of a platform for creating software applications, PaaS is the model for you. PaaS only requires you to handle the applications and the data. The rest of the components like runtime, middleware, operating systems, servers, storage, and others are handled by the cloud service providers. And finally, we have SaaS. SaaS, or Software as a Service, involves cloud services for hosting and managing your software applications. Software and hardware requirements are satisfied by the vendors, so you don't have to manage any of those aspects of the solution. If you'd rather not worry about the hassles of owning any IT equipment, the SaaS model would be the one to go with. With SaaS, the cloud service provider handles all components of the solution required by the organization. Time for a quiz now. In which of the following deployment models are you, as the business, responsible for the application, data, and operating system? 1. IaaS. 2. PaaS. 3. SaaS. 4. IaaS and PaaS. Let us know your answer in the comments section below. Coming back to cloud computing, some of the most popular cloud computing services in the market are AWS or Amazon Web Services, Microsoft Azure, and Google Cloud Platform. Want to learn more about them and how they differ from each other? Click on the top right corner for an analysis of how these service platforms are different from each other.
Hi there, I'm Sam from Simplilearn and I work as a multi-platform cloud architect and trainer. And let me welcome you to this learning video called What is Cloud Computing? Before cloud computing existed, if we need any IT servers or application, let's say a basic web server, it does not come easy. Now here is an owner of a business, and I know you would have guessed it already that he's running a successful business by looking at the hot and fresh brewed coffee in his desk and lots of paperwork to review and approve. Now he had a smart, not only smart looking, but a really smart worker in his office called Mark. And on one fine day he called Mark and said that he would like to do business online. In other words, he would like to take his business online, and for that he needed his own website as the first thing. And Mark puts all his knowledge together and comes up with this requirement that his boss would need lots of servers, database and softwares to get his business online, which means a lot of investment. And Mark also adds that his boss will need to invest on acquiring technical expertise to manage the hardware and software that they will be purchasing, and also to monitor the infrastructure. And after hearing all this, his boss was close to dropping his plan to go online. But before he made a decision, he chose to check if there are any alternatives where he don't have to spend a lot of money and don't have to spend acquiring technical expertise. Now that's when Mark opened this discussion with his boss, and he explained his boss about cloud computing. And he explained his boss the same thing that I'm going to explain to you in some time now about what is cloud computing. What is cloud computing? Cloud computing is the use of a network of remote servers hosted on the internet to store, manage, and process data rather than having all that locally and using local server for that. Cloud computing is also storing our data in the internet from anywhere and accessing our data from anywhere throughout the internet. And the companies that offer those services are called cloud providers. Cloud computing is also being able to deploy and manage our applications, services, and network throughout the globe and manage them through the web management or configuration portal. In other words, cloud computing service providers give us the ability to manage our applications and services through a global network or internet. Example of such providers are Amazon Web Service and Microsoft Azure. Now that we have known what cloud computing is, let's talk about the benefits of cloud computing. Now I need to tell you, the cloud benefits is what is driving cloud adoption like anything in the recent days. If you want an IT resource or a service now with cloud, it's available for me almost instantaneously, and it's ready for production almost the same time. Now this reduces the go live date, and the product and the service hit the market almost instantaneously compared to the legacy environment. And because of this, the companies have started to generate revenue almost the next day, if not the same day. Planning and buying the right size hardware has always been a challenge in legacy environment, and if you're not careful when doing this, we might need to live with a hardware that's undersized for the rest of our lives. With cloud, we do not buy any hardware, but we use the hardware and pay for the time we use it. If that hardware does not fit our requirement, release it and start using a better configuration and pay only for the time you use that new and better configuration. In legacy environments, forecasting demand is an full-time job, but with cloud, you can let the monitoring and automation tool to work for you and to rapidly scale up and down the resources based on the need of that hour. Not only that, the resources, services, data can be accessed from anywhere as long as we are connected to the internet. And even there are tools and techniques now available which will let you to work offline and will sync whenever the internet is available. Making sure the data is stored in durable storage and in a secure fashion is the talk of the business, and cloud answers that million-dollar question. With cloud, the data can be stored in a highly durable storage and replicated to multiple regions if you want, and the data that we store is encrypted and secured in a fashion that's beyond what we can imagine in local data centers. Now let's bleed into the discussion about the types of cloud computing. Very lately, there are multiple ways to categorize cloud computing because it's ever growing. Now we have more categories. Out of all these 6 sort of stand out, categorizing cloud based on deployments and categorizing cloud based on services. And again, under deployments, categorizing them based on how they have been implemented. Is it private, is it public, or is it hybrid? And again, categorizing them based on the service it provides. Is it infrastructure as a service, or is it platform as a service, or is it software as a service? Let's look at them one by one. Let's talk about the different types of cloud based on the deployment models first. In public cloud, everything is stored and accessed in and through the internet, and any internet users with proper permissions can be given access to some of the applications and resources. And in public cloud, we literally own nothing, be it the hardware or software. Everything is managed by the provider. AWS, Azure, and Google are some examples of public cloud. Private cloud, on the other hand, with private cloud, the infrastructure is exclusively for a single organization. The organizations can choose to run their own cloud locally or choose to outsource it to a public cloud provider as managed services. And when this is done, the service, the infrastructure will be maintained on a private network. Some examples are VMware Cloud, and some of the AWS products are very good example for private cloud. Hybrid cloud has taken things to the whole new level. With hybrid cloud, we get the benefit of both public and private cloud. Organizations will choose to keep some of their applications locally, and some of the application will be present in the cloud. One good example is NASA. It uses hybrid cloud. It uses private cloud to store sensitive data and uses public cloud to store and share data which are not sensitive or confidential. Let's now discuss about cloud based on service model. The first and the broader category is infrastructure as a service. Here we would rent the service, network, storage, and we'll pay for them in an hourly basis. But we will have access to the resources we provision, and for some we will have root level access as well. EC2 in AWS is a very good example. It's a VM for which we have root level access to the OS and admin access to the hardware. The next type of service model would be platform as a service. Now in this model, the providers will give me a pre-built platform where we can deploy our codes and our applications, and they will be up and running. We only need to manage the codes and not the infrastructure. Here in software as a service, the cloud providers sell the end product, which is a software or an application, and we directly buy the software on a subscription basis. It's not the infra or the platform, but the end product or the software or a functioning application, and we pay for the hours we use the software. And in here, the client maintains full control of the software and does not maintain any equipment. Amazon and Azure also sell products that are software as service. This chart sort of explains the difference between the four models, starting from on-premises to infrastructure as a service to platform as a service to software as a service. This is self-explanatory that the resource managed by us are huge in on-premises, that towards your left as you watch, and it's little less in infrastructure as a service as we move further towards the right, and further reduced in platform as a service, and there's really nothing to manage when it comes to software as a service because we buy the software, not any infrastructure component attached to it. There are lots of famous well-known organizations around the world. They have moved or have migrated to the cloud environment. Pinterest is one company which is one of the world's largest visual bookmarking tool with more than 70 million monthly active users. Now Pinterest was able to scale its business because it was all built on Amazon Web Services. With a company with less number of employees, Pinterest decided that they do not want to dedicate its staff time to manage a data center. Instead, Pinterest uses AWS, or they used AWS to manage their high performance social application and store more than 8 billion objects and 400 terabytes of data in AWS cloud using a service called Amazon Simple Storage Service, or in short Amazon S3. And not only that, they are running 225,000 instance hours a month, and they run that on Amazon compute service called Amazon EC2 or Amazon Elastic Compute Cloud. Spotify is another company that got benefited using AWS. It's an online music service offering, and it offers instant access to over 16 million licensed songs. Spotify needed a peculiar requirement. It needed a storage solution that could scale very quickly without incurring long lead times for upgrades. Long story short, Spotify used Amazon S3, which is Amazon Simple Storage Service, and Amazon S3 gave them the confidence in their ability and to expand their storage quickly while also providing high data durability. The third biggest company I want to mention is Netflix. It's the world's largest internet television network with more than 100 million members in more than 190 countries. Netflix uses Amazon Web Services for nearly all its computing and storage needs. Now that includes database, analytic, recommendation engines, video transcoding, and a lot more. Not only that, this company is planning to use AWS Lambda to build an automated or an rule-based self-managing infrastructure and replace some of their inefficient process to reduce the rate of errors and replace inefficient processes to reduce the rate of errors and save their valuable time. Expedia is another famous company that got benefited by using cloud. Expedia provides travel booking service through its flagship site called expedia.com, and not only that, they also run 200 plus travel booking sites around the world. Expedia is all on AWS, and by using AWS, Expedia has become more resilient with an high scalable infrastructure and better cloud services because it had offloaded the IT management to the cloud provider itself, in this case AWS. And because of this, Expedia's developers have been able to innovate faster while saving the company millions and millions of dollars. As next thing, let's talk about the different cloud providers. Amazon Web Services, AWS, is a cloud computing service provided by Amazon. It provides a mix of infrastructure as a service, IaaS, platform as a service, PaaS, and packaged software as a service called SaaS offerings. Microsoft Azure, formerly known as Windows Azure, is a cloud computing service by Microsoft, and it sort of specializes in using cloud for building, testing, deploying, and managing the applications through the servers throughout a global network that Microsoft manages. It also provides software as a service, platform as a service, infrastructure as a service, and it supports lots of different programming languages and tools and frameworks, including both Microsoft and third-party software and systems. IBM Cloud is a cloud computing service offered by IBM. IBM Cloud includes infrastructure as a service, software as a service, platform as a service. Now, the difference is here it offers through public, private, and hybrid cloud delivery models. VMware, on the other hand, is an subsidiary of Dell Technologies and provides cloud computing and platform virtualization software and services. It was the first commercially successful company to virtualize the x86 architecture. Google Cloud Platform, on the other hand, is offered by Google. It's a suite of cloud computing services that run on the same infrastructure that Google uses internally for its end-user products such as the Google Search and the YouTube you're familiar with. Alongside a set of managed tools, it also provides cloud services including computing services, data storage services, data analytics, and machine learning services. DigitalOcean, on the other hand, is headquartered in New York City with data centers worldwide. DigitalOcean provides developers cloud services that help to deploy and scale applications that run simultaneously on multiple computers. As of January 2018, DigitalOcean was the third largest hosting company in the world in terms of web-facing computers. Let's talk about cloud computing in AWS. Amazon Web Services, AWS, is a cloud computing service provided by Amazon, and these services are accessible over the internet. And because AWS provides infrastructure as a service, it's a flagship offering, we can create and deploy any type of application in the cloud on top of the IaaS that Amazon provides. And you know, the best part here is the subscriptions are pay-as-you-go type. You use less and pay less, and only for what you have used. You use more, pay more, but still less per unit for the service used. Attractive, isn't it? Now let's talk about the life cycle of the cloud computing solution. The very first thing in the life cycle of a solution or a cloud solution is to get a proper understanding of the requirement. I didn't say get the requirement, but said get a proper understanding of the requirement. It is very vital because only then we will be able to properly pick the right service offered by the provider. Getting a sound understanding, the next thing would be to define the hardware. Meaning choose the compute service that will provide the right support where you can resize the compute capacity in the cloud to run application programs. Getting a sound understanding of the requirement helps in picking the right hardware. One size does not fit all. There are different services and hardwares for different needs you might have, like EC2 if you're looking for IaaS, and Lambda if you're looking for serverless computing, and ECS that provides containerized service. So there are a lot of hardwares available. Pick the right hardware software that suits your requirement. The third thing is to define the storage. Choose the appropriate storage service where you can back up your data and a separate storage service where you can archive your data locally within the cloud or from the internet. And choose the appropriate storage. There is one separately for backup called S3, and there is one separately for archival, that's for Glacier. So you knowing the difference between them really helps in picking the right service for the right kind of need. Define the network that securely delivers data, video and applications. Define and identify the network services properly. For example, VPC for network, Route 53 for DNS, and direct connection for private P2P line from your office to the AWS data center. Set up the right security services, IAM for authentication and authorization, and KMS for data encryption at rest. So there are a variety of security products available. We got to pick the right one that suits our need. And there are a variety of deployment and automation and monitoring tools that you can pick from. For example, CloudWatch is for monitoring, autoscaling is for being elastic, and CloudFormation is define the management process and tools. You can have complete control of your cloud environment if you define the management tools which monitors your AWS resources and or the custom applications running on AWS platform. There are a variety of deployment, automation and monitoring tools you can pick from, like CloudWatch for monitoring, autoscaling for automation, and CloudFormation for deployment. So knowing them will help you in defining the life cycle of the cloud computing solution properly. And similarly, there are a lot of tools for testing a process like CodeStar and Code Build and Code Pipeline. These are tools with which you can build, test and deploy your code quickly. And finally, once everything is said and done, pick the analytics service for analyzing and visualizing the data using the analytics services, where we can start querying the data instantly and get a result. Now, if you want to visually view the happenings in your environment, you can pick Athena, and other tools for analytics are EMR and which is Elastic MapReduce and Cloud Search. Alright, enough of theory, and let's have a quick look at how two services in AWS, EC2 and S3, work together and benefits us. Here are two IT professionals talking to each other. One says, I have an application which takes a lot of storage and works only on Linux system, which I do not have at the moment. And the other one is a smart guy, and he immediately replies that he could use S3 to store data and retrieve data, and use EC2 for all his compute needs. And then the curious conversation builds up, and the first person wants to know what is EC2 and S3. And the second guy starts to explain that AWS EC2 is a web service that provides a secure and resizable compute capacity in their cloud. And EC2, it can also be used to launch as many virtual servers as we need. And about S3, he explains AWS S3 is a simple storage service provided by AWS. And about S3, he explains further, saying that using Amazon S3, we can store and retrieve any amount of data at any time on the web. Alright, so the very first thing is to have an AWS account. So create an AWS account. And second thing is to create an AWS S3 bucket and upload the files there. The files that EC2 server is going to pull from will get stored in S3 as first thing. Alright, so the first thing is to create an S3 bucket. So let's create an S3 bucket and let's call it as website bucket. And these names will have to be unique. So let's see if this bucket name is available. It says bucket name already taken or already exist. So let me top it up with SL, meaning simply learn. Alright, so we were able to create a bucket, and in that bucket let me upload a content. That basically is going to be my index file that's going to go and sit in my web server. So let me also make it public and view it. Alright, so this is the content that I have stored in my S3, and this is the content I'm going to push to my EC2 server. Alright, second step, create an AWS S3 bucket and upload files. We're done with that. Third is to create an EC2 instance. That's, in other words, create an virtual machine in the cloud. Let's go and create it. Alright, the third thing is to create an EC2 instance. So let's create an EC2 instance. It's plain and it's very simple. I'm going to keep everything as defaults here. Alright, so I've launched an EC2 instance. As you see, it's running. I also have an IP address, public IP address here. With that, I have logged into this EC2 instance, and I'm in the folder /var/www/html, and as you see, there is nothing in there at the moment. And this server also has Apache installed in it. As you can see, I browsed to the IP address of the EC2 instance, and it's showing a page which is the default Apache page. Alright, if I had any files in this folder, that would get shown as the web page instead of the default page. Our task is to save files in S3 and move them to the EC2 instance. So S3 is going to act as a storage or a repository or a source code control in this example. Alright, so let's do that. Alright, the third step is to create your EC2 instance, and that's what we have done. And the EC2 instance has no files in it. And the fourth step is to synchronize the source code bucket with the EC2 instance. Let's do that. The actual command to do that would be AWS S3 sync, and then the name of the bucket from which we're going to pull the code, and the folder in which we're going to put the code or the data. Alright, so it has downloaded something. Look at that. And now if we go back to the test page and do a refresh, there you go. It's showing the page that it pulled from S3. So here I can use S3 as the source code control bucket, and any information that I put in there will get reflected in EC2 instance once I do a sync every day. And that's how I use S3 as my storage for EC2. Alright, finally we were able to synchronize S3 bucket and the EC2 instance. And we were also able to view the results in the web browser of the EC2 instance. The data was copied from S3 to the EC2 instance, and that we were able to view from the web browser.
AWS, Azure and GCP are three of the world's largest cloud service providers. But how are they different from each other? Let's find out. Hey guys, I'm Rahul and I'll be representing Amazon Web Services.
I'm Chinmayi and I'll be representing Microsoft Azure.
And I'm Shruti and I'll be representing Google Cloud Platform. So welcome to this video on AWS versus Azure versus GCP.
Talking about market share, Amazon Web Services leads with around 32% of the worldwide public cloud share.
Azure owns up to 16% of the worldwide market share.
And GCP owns around 9% of the world's market share.
Let's talk about each of these service providers in detail. AWS provides services that enable users to create and deploy applications over the cloud. These services are accessible via the internet. AWS, being the oldest of the lot, was launched in the year 2006.
Azure, launched in 2010, is a computing platform that offers a wide range of services to build, manage, and deploy applications on the network using tools and frameworks.
Launched in the year 2008, GCP offers application development and integration services for its end users. In addition to cloud management, it also offers services for big data, machine learning, and IoT.
Now let's talk about availability zones. These are isolated locations within data center regions from which public cloud services originate and operate. Talking about AWS, they have 69 availability zones within 22 geographical regions. This includes regions in the United States, South America, Europe, and Asia Pacific. They are also predicted to have 12 more additions in the future.
Azure, available in 140 countries, has over 54 regions worldwide grouped into 6 geographies. These geographical locations have more than 100 data centers.
GCP is available in 200 plus countries across the world. As of today, GCP is present in 61 zones and 20 regions, with Osaka and Zurich being the newly added regions.
Now let's talk about pricing. These services follow the pay-as-you-go approach. You pay only for the individual services you need for as long as you use them without requiring long-term contracts or complex licensing. Now on screen, you can see the pricing for each of these cloud service providers with respect to various instances like general purpose, compute optimized, memory optimized, and GPU. Now let's talk about the compute services offered. First off, we have virtual servers. For AWS, we have EC2. It is a web service which eliminates the need to invest in hardware so that you can develop and deploy applications in a faster manner. It provides virtual machines in which you can run your applications.
Azure's virtual machines is one of the several types of computing resources that Azure offers. Azure gives the user the flexibility to deploy and manage a virtual environment inside a virtual network.
GCP's VM service enables users to build, deploy, and manage virtual machines to run workloads on the cloud.
Now let's talk about the pricing of each of these services. AWS EC2 is free to try. It is packaged as part of AWS's free tier that lasts for 12 months and provides 750 hours per month of both Linux and Windows virtual machines.
Azure Virtual Machine Service is a part of the free tier that offers this service for about 750 hours per month for a year. The user gets access to Windows and Linux virtual machines.
GCP's VM service is a part of a free tier that includes micro-instance per month for up to 12 months.
Now let's talk about Platform as a Service or PaaS services. For AWS, Elastic Beanstalk is an easy-to-use service for deploying and scaling web applications and services developed with Java, .NET, Node.js, Python, and much more. It is used for maintaining capacity, provisioning, load balancing, auto-scaling, and application health monitoring.
The PaaS backbone utilizes virtualization techniques where the virtual machine is independent of the actual hardware that hosts it. Hence, the user can write application code without worrying about the underlying hardware.
Google App Engine is a cloud computing platform as a service which is used by developers for hosting and building apps in Google data centers. The App Engine requires the apps to be written in Java or Python and store data in Google Bigtable and use the Google query language for this.
Next, let's talk about virtual private server services. AWS provides Lightsail. It provides everything you need to build an application or a website along with the cost-effective monthly plan and minimum number of configurations.
In simple words, VM Image is a more comprehensive image for Microsoft Azure virtual machines. It helps the user create many identical virtual machines in a matter of minutes.
Unfortunately, GCP does not offer any similar service.
Next up, we have serverless computing services. AWS has Lambda. It is a serverless compute service that lets you run your code without facilitating and managing servers. You only pay for the compute time you use. It is used to execute backend code and scales automatically when required.
Azure Functions is a serverless compute service that lets you run event-triggered code without having to explicitly provision or manage infrastructure. This allows the users to build applications using serverless simple functions with the programming language of their choice.
GCP Cloud Functions make it easy for developers to run and scale code in the cloud and build event-driven serverless applications. It is highly available and fault-tolerant.
Now let's talk about storage services offered by each of these service providers. First off, we have object storage. AWS provides S3. It is an object storage that provides industry standard scalability, data availability, and performance. It is extremely durable and can be used for storing as well as recovering information or data from anywhere over the internet.
Blob storage is an Azure feature that lets developers store unstructured data in Microsoft's cloud platform. Along with storage, it also offers scalability. It stores the data in the form of tiers depending on how often data is being accessed.
Google Cloud Storage is an online storage web service for storing and accessing data on Google Cloud Platform infrastructure. Unlike the Google Drive, Google Cloud Storage is more suitable for enterprises. It also stores objects that are organized into buckets.
Amazon provides EBS or Elastic Block Store. It provides high-performance block storage and is used along with EC2 instances for workloads that are transaction or throughput intensive.
Azure Managed Disk is a virtual hard disk. You can think of it like a physical disk in an on-premises server but virtualized. These managed disks allow the users to create up to 10,000 VM disks in a single subscription.
Persistent storage is a data storage device that retains data after power to the device is shut off. Google Persistent Disk is durable and high-performance block storage for GCP. Persistent Disk provides storage which can be attached to instances running in either Google Compute Engine or Kubernetes Engine.
Next up, we have disaster recovery services. AWS provides a cloud-based recovery service that ensures that your IT infrastructure and data are recovered while minimizing the amount of downtime that could be experienced.
Site recovery helps ensure business continuity by keeping business apps and workloads running during outages. It allows recovery by orchestrating and automating the replication process of Azure virtual machines between regions.
Unfortunately, GCP has no disaster recovery service.
Next, let's talk about database services. First off, for AWS, we have RDS or Relational Database Service. It is a web service that's cost-effective and automates administration tasks. Basically, it simplifies the setup, operation, and scaling of a relational database.
Microsoft Azure SQL Database is a software as a service platform that includes built-in intelligence that learns app patterns and adapts to maximize performance, reliability, and data protection. It also eases the migration of SQL Server databases without changing the user's applications.
Cloud SQL is a fully managed database service which is easy to set up, maintain, and administer relational PostgreSQL, MySQL, and SQL Server databases in the cloud. Hosted on GCP, Cloud SQL provides a database infrastructure for applications running anywhere.
Next, we have NoSQL database services. AWS provides DynamoDB, which is a managed, durable database that provides security, backup and restore, and in-memory caching for applications. It is well known for its low latency and scalable performance.
Azure Cosmos DB is Microsoft's globally distributed multi-model database service. It natively supports NoSQL created for low latency and scalable applications.
GCP Cloud Data Store is a NoSQL database service offered by Google on the GCP. It handles replication and scales automatically to your application's load. With Cloud Data Store's interface, data can easily be accessed by any deployment target.
Now let's talk about the key cloud tools for each of these service providers. For AWS, in networking and content delivery, we have AWS Route 53 and AWS CloudFront. For management, we have AWS CloudWatch and AWS CloudFormation. For development, we have AWS CodeStart and AWS CodeBuild. For security, we have IAM and Key Management Service.
For Microsoft Azure, networking and content delivery, we have Content Delivery Network and ExpressRoute. For management tools, we have Azure Advisor and Network Watcher. For development tools, for management, we have Azure Advisor and Network Watcher. For development, we have Visual Studio IDE and Azure Blob Studio. For security, we have Azure Security Center and Azure Active Directory.
For GCP, we have the following tools. For networking and content delivery, we have Cloud CDN and Cloud DNS. For management, we have Stack Driver and GCP Monitoring. For development, we have Cloud Build and Cloud SDK. And finally, for security, we have Google Cloud IAM and Google and Cloud Security Scanner.
Now let's talk about the companies using these cloud providers. For AWS, we have Netflix, Unilever, Kellogg's, NASA, Nokia, and Adobe.
Pixar, Samsung, eBay, Fujitsu, EMC, and BMW, among others, use Microsoft Azure.
So as seen on your screens, the companies that use GCP are Spotify, HSBC, Snapchat, Twitter, PayPal, and 20th Century Fox.
Let's talk about the advantages of each of these services. Amazon provides enterprise-friendly services. You can leverage Amazon's 15 years of experience delivering large-scale global infrastructure, and it still continues to hone and innovate its infrastructure management skills and capabilities. Secondly, it provides instant access to resources. AWS is designed to allow application providers, ISVs, and vendors to quickly and securely host your applications, whether an existing application or a new SaaS-based application. Speed and agility. AWS provides you access to its services within minutes. All you need to select is what you require and you can proceed. You can access each of these applications anytime you need them. And finally, it's secure and reliable. Amazon enables you to innovate and scale your application in a secure environment. It secures and hardens your infrastructure. More importantly, it provides security at a cheaper cost than on-premise environments.
Now talking about some of the advantages of Azure. Microsoft Azure offers better development operations. It also provides strong security profile. Azure has a strong focus on security, following the standard security model of detect, assess, diagnose, stabilize, and close. Azure also provides a cost-effective solution. The cloud environment allows businesses to launch both customer applications and internal apps in the cloud, which saves on IT infrastructure costs. Hence, it's OpEx friendly.
Let's now look at the advantages of GCP. Google bills in minute-level increments, so you only pay for the compute time you use. They also provide discounted prices for long-running workloads. For example, you use the VM for a month and get a discount. GCP also provides live migration of virtual machines. Live migration is the process of moving a running VM from one physical server to another without disrupting its availability to the users. This is a very important differentiator for Google Cloud compared to other cloud providers. GCP provides automatic scalability. This allows a site's container scale to as many CPUs as needed. Google Cloud Storage is designed for 99.9% durability. It creates server backup and stores them in a user-configured location.
Let's talk about the disadvantages of each of these services. For AWS, there's a limitation of the EC2 service. AWS provides limitations on resources that vary from region to region. There may be a limit to the number of instances that can be created. However, you can request for these limits to be increased. Secondly, they have a technical support fee. AWS charges you for immediate support, and you can opt for any of these packages. Developer, which costs $29 per month, Business, which costs more than $100, and Enterprise, that costs more than $15,000. It has certain network connectivity issues. It also has general issues when you move to the cloud, like downtime, limited control, backup protection, and so on. However, most of these are temporary issues and can be handled over time.
Talking about some of the disadvantages of Microsoft Azure. Codebase is different when working offline and it requires modification when working on the cloud. PaaS ecosystem is not as efficient as IaaS. Azure Management Console is frustrating to work with. It is slow to respond and update and requires far too many clicks to achieve simple tasks. Azure Backup is intended for backing up and restoring data located on your on-premises servers to the cloud. That's a great feature, but it's not really useful for doing bare metal restores of servers in a remote data center.
Let's now look into the disadvantages of GCP. So when it comes to cloud providers, the support fee is very minimal, but in the case of GCP, it is quite costly. It is around $150 per month for the most basic service. Similar to AWS S3, GCP has a complex pricing schema. Also, it is not very budget friendly when it comes to downloading data from Google Cloud Storage.
Today we're going to delve into Git and what it actually is and how it fits within your DevOps stack. So a little scenario before using Git. One of the challenges that a lot of developers and development teams would have had is developers would be working on different types of code, whether it was database code, whether it was Python, or whether it was Java or .NET, and they would have a central server that they would be pushing all of their source code in. But there was little or no communication that was actually going on in between all the developers. The challenge you had with that scenario is that when people would be checking in code, you could be like, there'd be conflicts and you'd have to roll back different code versions. And this is really kind of the challenge that Git addresses. Git is a tool that allows all of the developers, no matter what stack they're working in, to have access to all of the code. And it makes it much more effective at being able to have development teams work on small, medium, or even massive applications. And some of the biggest applications out there are managed through a Git distributed server environment. So let's jump into what we'll be covering so you have a clear understanding of the value that you're going to get out of watching this presentation. So we're going to go through DevOps and the tools we have available for DevOps. We'll talk about what version control means within a DevOps environment and cover the two different types of version control, centralized and distributed. And then we're going to zero in on Git, which is a really fantastic distributed version control system. And we're going to go through and understand the features, workflow, branches, and commands in Git. We're going to give you a demo and then summarize all of the activities at the end of the presentation. So, what is DevOps? Well, this is one of my favorite questions. I love the idea of what DevOps is. So DevOps really is a culture of being able to deliver solutions faster, where your development teams and your operation teams work effectively together. The idea is to be able to continuously build out solutions and have testing codes that's built into your solutions, so that no matter where they are in the stage of the integration and deployment lifecycle, they're always being tested and you can always have code getting ready to be released out. The idea is that instead of having big releases that you would have maybe once every 2 weeks or once a month, that you would actually have a continuous stream of releases, because you always have code that is being tested, you have your network that's being tested, you have your environment being tested, and you'll be able to provide feedback directly to the appropriate person, whether they're in devs or whether they're in ops, to be able to be successful at being able to deliver solutions faster. The bottom line, your dev team thinks like operations, and your operations team begin to think like developers. It's really a fantastic way of being able to speed up delivery and have your team just think and feel and act in a different cultural environment. So let's have a look at some of the tools that are available to you in DevOps environments. If we look at DevOps, it's really kind of split into two areas. The dev side, you have building, code, planning, and testing. And then on your ops side, you have release, deployment, operating, and monitoring. But the tools really all interact with each other. And what's really great is that the tools are either open source or very, very low in cost. And in fact, most of the tools that you're seeing in front of you right now are open source tools, which means there's no licensing to you, and you can actually effectively manage them and implement them within your team right now. So let's have a look at some of the dev tools that you have for doing code versioning. And so Some of the tools that you may have used in the past include Subversion, Team Foundation Service, and Git. These are all different types of version control software that you have out there. One of the oldest ones is Subversion. It's a centralized version control system. It's one of the tools I used years ago. It really is good at doing what it's supposed to do, which is just a very simple version controlled solution. It's open source, so it's free. There's no licensing. There are challenges with working with it because it is a centralized tool rather than a distributed tool, and we'll get into that in a little bit. But for a very basic version control system, it does what you want it to do. Team Foundation Service Solutions is something that many of you in Microsoft world may have been using for a long time. And the thing that's great about TFS is that it's built right into the Microsoft environment. It's the server side, the services side of building out your solutions with Microsoft. Just recently, in the last couple of weeks, at the beginning of September 2018, Microsoft actually just rebranded TFS as Azure DevOps, and so you have Azure Pipelines, and there are 5 now Azure tools that actually replace TFS. But these are all tools that are very similar in concept. The old TFS tools are very similar to the centralized SVN tools, whereas the new tools that are part of Azure are actually much more aligned with Git. So what you're seeing is Microsoft moving from the centralized server to a distributed server with their new Azure DevOps tools, which is fantastic news for every developer listening to this. And then we have Git, and Git is a distributed version control system. It is, again, open source, which means that you can start using it right now without fear of having to have any costs or any penalties. And the thing that's really good about it is that you can use it for almost any kind of digital project. And what it's good at is being able to create that historical record and versioning of your source code, whether you're doing a web application, a mobile application, or you're actually building a Python script for a machine learning solution. So let's dig into what version control systems are and how they can be of value to you. So the role of a version control system is to allow developers to be able to check in their files into a repository. And here you can actually see how we can check in 3 files into a repository, and that repository then becomes a snapshot or a historical record of the files that we're working on. And you want to be able to have it so that the repository is flexible enough so that as you want to be able to scale and add in new files or new versions of a file, that you can actually do that easily within your VCS environment. And the goal is to be able to constantly have each of these versions available so that anybody that wants to be able to check out the file can actually have the latest version or see a history of how that file became what it is today. Let's look at centralized version control systems, and then we'll compare it against distributed version control systems. So a centralized version control system has a central server where all the files are stored, and everybody has to check in and check out from that centralized server, and all of the versions are managed within that server environment. The problem is that if that central server crashes, which doesn't happen but very often, but it can happen, you end up losing all of your files. And I was actually on a project where that actually happened to us, and we lost 6 months of history of how the application was created. Fortunately for us, we actually had a backup, but it didn't have all the historical data. So we were able to at least continue working, but we just lost a lot of files, and it took a while to get back into place. So let's now look at and compare this to a distributed version control system. With a distributed version control system, you still have a centralized server that manages the files. But the difference is that as a developer, you check out all of the files for a project. So you can actually manage the whole project locally on your development machine and make your changes. And then you can just check in and out the changes that you've made to the centralized server. The opportunity you have here is that the server itself, if it goes down, you're not going to be in a situation where you lose all of the history, because everybody that's working on the actual application has all of the versions of the code locally on their machine. Now, one of the more popular distributed version control systems that out there is Git. I mean, it really is probably the most popular by a margin compared to a system out there. So, let's dig into, what actually is Git. So Git is a version control system for managing files, and as a developer, you have a Git client on your machine and you're able to make changes and create local repositories of a program on your computer, and then you can sync up with a remote service such as GitHub or GitLab or the new Azure Labs environment, where you can actually store files remotely and then allow remote teams to have access to those changes in the actual application you made. So you can track your changes easily. The tool is inherently distributed, so it makes it very easy to manage the code for large teams. And you can bring people in very quickly, and you can have people come in as specialists and spin them up quickly and have them work on a piece of the code and then drop them out of the project. If you want to have a check on how this works, go and start contributing to any of the many thousands of open source projects like GitHub, where you can go in with your Git tools and just contribute to those projects. And then finally, one of the things that I really like with Git is that it's not a linear development approach. It's not starting from A and going to Z. It's a non-linear approach, which allows you to have branches that people are working on in parallel to your master branch, where people are actually doing the delivery of the production code. So let's step through some of these features. So Git, as you can imagine, the first thing it does is track history. That's probably the most important part of having a version control system. It's free open source. You can actually go and use it right now. There are no costs for actually using it. It is a non-linear environment that allows people to be able to build out new features in parallel to the master branch, so that you can be constantly having the master code out there and adding in new features without breaking the code. And you can automatically create backups because each developer has a version of the code remotely. It's incredibly scalable. Some of the biggest projects out there now are being managed through Git. And because of this scale, the collaboration becomes a byproduct of teams working together. And branching just is so much easier within Git. So as you can see, this whole thing leads to a very effective distributed environment. So let's step through some of the workflow that we have available for Git. So the way that Git works is that you, as an operator, as a developer, you have the Git client on your local development machine, whether it's a Linux machine, a Mac, or a PC, and you connect to a remote server and you pull down the latest working copy, and then you're able to make all of your changes locally, and you can modify the codes, you can review changes, and you can commit those codes to your Git repository that you have locally, and then you can push those changes back up to the remote server. And as soon as you push them into the remote server, those changes then become available to everybody else working on the project. So they can be constantly keeping everybody updated on all the work that is happening. So, typically the way that it would work is, you would start off with having the working file, the working directory that you have locally, and then you would stage those files into a staging area, and then you get those files ready to be committed to your Git repository. And these are all actions that you would do locally and then connect to a remote server. And then later, when you go back into work on your project, the first thing you should always do is check out that code so that you always have the latest version of the code and everybody's kept in sync. So let's talk about branching in Git. So the way that branches work is that if you imagine you're working on a project, and projects always have a tendency of getting bigger than you imagine. And what you want to be able to do is keep that main product working and keeping it working effectively. But if you want to be able to add a feature to that product, you may have 2 or 3 different groups that are working on multiple features simultaneously. And what you want to be able to do is give them the freedom to work on those individual features. And the way you do it in Git is that you can create branches off the master, and while you're off the main branch, which is called the master. And so each person could be working on their own separate branch, and then when they want to, they can then later merge those branches back into the main master. And all this time, the main master still works and still able to produce the right code for the customer, but at the same time, it allows the developers the freedom to be able to write in their new features. And so we can look at this in a little bit more visually with the master branch, and we can put in small features and large features, and we can then merge them back as we need to. So this kind of covers some of the commands that we have in Git. So the first command you'd want to use is called git init, and that's allowing you to go into a folder on your local PC or your local Mac and convert that folder into a local Git repository, and that creates that repository. Then you want to be able to make changes to that repository, and the commands you'd be using in this instance would be add, commit, or status. You want to be able to sync your repositories with the remote server. So be able to put the code that you have on your computer on the remote server, you use push. You want to get the code from the remote server, you'd use pull and then add origin. And then if you want to do parallel development from the master branch, the main branch, you would use branch, merge, or rebase as ways to be able to do parallel development. And now we're going to go through and do a demo on Git. So we're going to do a demo on Git so you can feel comfortable running the commands in the interface and you're able to get Git running correctly in your environment. So the first thing we're going to do is we're going to set up which version of Git that you have, and then we're going to see if we can establish some global configurations within your Git environment. And we're going to do sandeep.dash as the name, the email address is sandeep.simplylearn, and then we're going to do a list of the different configuration settings we have. So to check the version of Git that we have, we do git -- version in our terminal or command line window. You can also use PowerShell. That'll actually get you running in the same environment as well. All of these tools are going to be command line tools. And then the next thing we're going to do is we're going to assign some global usernames and a global email address so that we can actually access the Git account itself locally on the device. And so we're going to put in config -- global user.name Sandeep, and then git config -- global user.email and sandeep.d@simplylearn.net. And now we're going to check the list of usernames and email IDs in our configuration environment with -list, and you'll see that we have everything in there correctly. Here is our username right here, and our name and our email ID. So if you need any help when you're actually doing any of your work in Git, all you have to do is do git help config or git config -- help, and this will allow you to actually get access to the help screens. So let's just go and type that in, git help config, return, and this takes us to the help page that's running locally on your device. And here we have a breakdown of all the different commands and what those commands actually do within a Git configuration. And we can go ahead and we can do git config -- help, and that will actually take us to the same page. So two ways of doing the same thing. So we're going to go ahead and we're going to create a test repository on our local system, and we're going to do that with make directory called test, and then we're going to move our cursor within command window, terminal window, to the test folder, and then we're going to initialize that folder to become a Git repository. So let's go ahead and do that. So we're going to make a new directory and we're going to call it test, and we're going to move the cursor so it's actually in the test folder. We do cd change directory to test, and you can see now we're actually in the test folder. And now what you have to do is initialize this folder as a Git repository. And so we're going to do this as git init, and it's now a new Git instance that we can actually now use for managing our Git environment. So we're going to create a new file and we're going to call it info.txt, and we're going to put some content in it, and we're actually going to put it in the folder that we've just created so you can actually see what it's like to test out the Git environment with a file that hasn't been checked into it yet. So let's go ahead and do that. So we open up our folder directory, and here you can see we have the test folder, and we're just going to go ahead and create a default test file. So right click, text, new document, info.txt, open that, and you can put really whatever you want in here. We're just going to put in this information right now. Name equals Sam, registration number 12479, and save that file, close it out. Now if we actually go ahead and run a git status command, you'll see that the info.txt file is in red. That's because that file has not actually been checked into the project. It's a new file that we've added, but it hasn't been committed yet into the Git repository. So let's go ahead and see what it takes to actually add the file to the Git repository that we just created. So we're going to do that by doing git add info.txt, and then we're going to commit that into the history of that Git repository. So it now has version control, and we can start doing forking and other kind of similar activities when we connect later to our GitHub Git environment. So we do git add info.txt, and remember we're actually still in the test folder, so it's going to look for that file in that folder and just add it in. And now if we go ahead and do get status, we'll actually be able to see that the info.txt file is in an active color. First of all, we have to commit it, so we go git commit -m, and then we're going to commit, and we add in some quick text here. You can write whatever you want. Committing the text file is now actually committed into the Git repository, and it's still running locally on your PC. So we're going to go make some changes to the file, and we're going to save it, and we want to be able to see how we can use Git to compare the differences between the two files. So let's go over, and we're going to make some changes to the info.txt file. Here we are. Here's info.txt. We're just going to add in a new line. We're going to add in the line address, and we're going to save that file. And now when we go over to Git, we're going to be able to review the difference. So we're going to do git diff, and here you actually see that we've added in a new address file. So now you can actually see this is the difference between the two documents. Now, as you can imagine, when you have code, this would become more elaborate, where actually will show you code that's been pulled out if you've reduced any of eliminated any code, or if you added in new code. Really useful. So we're going to go ahead and add our Git username to a remote location, so we can actually start testing out the file that we've created into a remote repository. In this case, we're going to use GitHub, and you'll be able to see how we can actually then save that file into a Git repository that somebody else could then access and be able to make edits to. So let's just go ahead and make those changes. So git config -global user.username, and we're going to do simply learn, and that will associate it with this Git repository that we've just created locally. So simply learn -github. So simply learn GitHub is the username that we use on GitHub. So we're going to go over to GitHub. Here we are in GitHub, and then correct new repository. And then, as you can see, we're in simply learn -github, and we're going to call the new repository test. We're going to make it public so anybody can access it, and you'll see that it automatically adds a README file, and we have our test environment set up correctly. So we'll go ahead and copy the URL link, which is github.com simply learn -github /test.git. Copy that, and we'll go back over to our command line window. And so now we're going to add the username to the GitHub configuration. So what we're doing is we're connecting the local repository to the remote repository. So we type git remote add origin, and then we'll paste in the address. And this then allows us to connect the local repository that we created in the test folder with the remote repository. And now we're connected. So now that we've connected, we can actually push the file that we have in the local repository on your PC or Mac to the remote repository in the GitHub server environment. So let's go ahead and do that. So we're going to do git push, and push is the command to push the documents from the origin, which is the local file, to master, and master is a remote file. Hey, and there we are. Success. So what we have now is the file that we just created in our local Git repository is actually now in the remote repository as well, so anybody can access it. So let's go have a look at that. So we're going to refresh the GitHub page, and hey, there we are. There's info.txt has been uploaded, and we're ready to go. That's great. That's what you should be seeing. So refreshing your web page on the remote GitHub folder, and it could be any Git service, but just happen to be using GitHub because it's free to use. You'll be able to see that the local file has been installed and is now part of the Git repository in the remote server. So what we're going to do now is we're going to create 3 more files, and we're just going to call them info.txt, info2, and info3, and then we're going to push them out to the remote server, and we're going to merge everything together into a single environment. So let's go ahead and create those 3 files, and we're just going to add those into the folder. So let's go ahead, create new text document, info1, and then we're going to create info2, and then info3. Get my typing right here. Okay, here we go. There we are. Okay, I'm opening info3, and I'm just going to enter some text in here. And what we're going to do is illustrate how we can do branching. And each of these files I'm going to save and then close out. And now I can go over, and so let's create a new branch, and we're going to call this one first_branch. And we go git branch first underscore branch, and this will be a new branch of the code environment that we're creating. And so hit return, and that allows us to create a new branch. And so what we do is we're going to move to the new branch. So we're going to do get checkout first underscore branch, and that allows us to move into that branch. And you see that info.txt is already there, which is good. That's what we want to see. Now what we need to do is add in the new documents. So here we have the different steps we've taken. We created a branch, we moved to the new branch, and now we're going to go ahead and add the info3txt to that branch so you can actually see everything coming together. And we're going to go at get add info3.txt. So we're just adding a file like we were previously with our initialization, our first initial Git folder, and that file has now been added to the first branch. So we're going to go ahead and commit the file to the first branch, and then we're going to merge the documents into the master branch so we have everything together. So let's go ahead and do those steps. We're going to do the commit first, and then we're going to merge everything together. All right, so we do git commit -m, and we'll just put in, we're just going to say made changes to first branch, and that's just documentation so that we know what we've done. And there we are, we've committed the file. So we had that file info3txt committed, and now we're going to go ahead and merge the files into the main master, and so we can actually have everything together as one consistent environment. And we do that by typing in, so this lists out what we have in our master file. So we just do ls, and that shows everything in the folder, and we have info.txt, info1txt, info2txt, and info3txt are now all in the first branch. So let's go ahead and we're going to merge. Okay, so actually before we merge, we have to check out the master branch. So we do git checkout master. So it gets us into the master branch, and you'll see that we have just one file there, info.txt. So we're going to list out the files in the master branch. And so what you'll see is info.txt, info1text, and info2text are there, but info3text isn't there because that was created in a separate branch. So let's go ahead and merge the first branch into the master branch. So we do git merge, and we do first underscore branch, and there we are, we've merged it in, and excellent, that looks good. So let's go ahead and list out the files that we have in the master branch, and we do ls, and then you'll see that we have 4 files, including the info3.txt that we had in a separate branch, now all in the master branch.
Welcome to Git Commands. Git is one of the most popular distributed version control tools of recent times, and like any other distributed version control tool, it allows us to perform various version control tasks without really needing a network connection. Before I jump into my demonstration, let me spend some time explaining to you the Git client-server working model. What does it take for a couple of users to collaborate and start working with Git? The bare minimal thing that any user would need in order to start working with Git is something called as Git Bash or the Git client. This comes as an installer for all popular operating systems like Windows, all flavors of Windows, Linux, macOS, and other operating systems. So once you install Git Bash, you get a command line utility using which you can fire up your Git commands and ensure that you can bring up repositories. You can work with these repositories by adding files to it, committing changes to it, and all those Git commands would work perfectly well. So you can bring up a small repository and you can work with your repository using this Git Bash. But what does it take for you to share this repository with another user who has also got Git Bash installed on his system? This is where you would need something called as a Git server. So for user 1 or one user to share his repository with another user, he would need to collaborate using something called as a Git server. So in the present market, there are a bunch of Git servers which are popularly available. Some of them are free, some of them come with a cost because they are licensed. A bunch of these servers that I can think of are GitHub, which is one of the most popular Git servers that is around in the market for a long time now. It comes with 2 variants. One is the cloud hosted one, which is the github.com. And then the other one is an enterprise server, which comes as a black box that can be installed into your data centers. So typically organizations who don't want their source code to be put up on the cloud would go for this GitHub enterprise servers, wherein they buy these servers and these servers are hosted on their data centers. other popular variant of the Git server is Bitbucket. This is from the famous Atlassian products, and it integrates very well with all other Atlassian products like Jira. In recent times, there's one other variant of the Git server called GitLab, which is getting very popular these days because GitLab not just provides a Git server, it also provides something called as a runner. This is a part of the continuous integration strategy where as soon as you have a source code check-in that is going in, you have this runner that kicks up and builds your particular project. So all these are bundled together in a GitLab. And GitLab also provides you with a community edition which is almost free of cost. Having said that, there are a bunch of these tools available. For my demonstration, what I'm going to do is I've already registered myself on the github.com by providing my username and my password. And I'm going to use a free account. So whatever repositories that I'm going to put up on this server is all public by default. So I've already registered myself by using my username or my email ID and my password. So this set of authentication is also referred to as HTTPS authentication. So in order for me to share my repository with say user 2, the first thing that I got to do is have an access to a Git server where both user 1 and user 2 are set up. So once I have that, I can push my repository onto this server and provide right kind of access so that user 2 or the other developer who wishes to collaborate with me on this repository can use his credentials as long as he's registered properly on the Git server. He can use his credentials and pull down this repository and work with this repository. So this is the HTTPS way of authenticating and sharing repositories. Another popular way of sharing repositories or working with each other is called as SSH authentication. As many of you would know, SSH means nothing but creation of a private and a public key. A bunch of keys, public and private, are created on the client machine. While I create keys, I will be asked for a passphrase. I need to type in a passphrase and remember my passphrase. And then I take this public key and kind of post it onto my account within my Git server, so that whenever I'm going to connect next time using my command prompt or any of the tools, it's going to challenge me for my passphrase. As long as I remember my passphrase correctly, I can authenticate myself and get into the server. So both HTTPS and SSH are popular ways of communicating with the Git server. Having said this, let me just get started by installing the Git bash on my local system and then fire up some of these Git commands and build up some repositories, make some changes in my repository, commit these changes, and later use my GitHub credential to connect to my GitHub server and push my repositories out there. Let me now go ahead and find my Git bash for my Windows so that I can go ahead and install it. So I just type in Git client for Windows, open up a browser and type in for this. The first one that I find is a GUI tool. I don't need this GUI client, I need this one. So this is the Git client or the Git bash that I was referring to. It's about 40 megs, and let me just download this. Pause this video for some time so that the download happens and come back to you once I have the download. The download seems to be complete. When I'm recording this video, the version that I have, the latest version that is there is 2.19.0, and this is a 64-bit version for Windows. So I've got that downloaded. Let me go ahead and find it and install this exe. Alright, I go ahead choosing all the default options. I want it to be installed in C: program files under the Git folder. Everything looks good for me. I'm not going to make any changes here. Git bash from Windows. Yes, I may want to use git from Windows command prompt. That sounds good for me. OpenSSH, that's fine. Looks good. Looks good. No, I don't want any of these new features. So what I'm doing is installing the Git bash or the Git client so that I can start using my Git commands. And the version that I'm using is 2.19.0, which as I record this video, this happens to be the latest version. Alright, so looks good. I don't want to see the release notes. I'll say launch Git bash. So what I get is this window. So this is the Git command prompt. So let me check if everything is looking good. Say Git version, it sounds good. Say Git help. Alright, a lot of Git help commands. Everything looks good. So I ended up installing the git bash, I can go ahead with all other commands. Now that I have git bash installed on my system, let me open up a git bash prompt and start using it. But before I do anything, I just need to configure it for the first time, stating what would be the username and the email ID with which I want the git bash to be configured with. The command to do that is git config -- global, which means that this setting that I'm going to set would be a global setting. User.name, and the name of the user would need to be specified within a double quote. In my case, I am using a Simplilearn account, which is the official account, and this is the particular username of this account. The other setting is nothing but git config -- global. This is also a global setting, and this would be the email ID. The email ID need not contain a double quote. So in my case, this is the email ID that I would be setting up Git to work with. All right, let me check if the configurations were set correctly or not. All right, if you see this, the username and the email ID has been picked up the way I wanted it to be picked up. Looks good so far. All right, so what do we do next? By default, whenever you open up the Git prompt, you're placed into your home directory. Let me create a folder here, which would be a repository folder from where I'm going to create all my multiple Git repositories. So I will create a folder called, let's say, git_demo. All right, there's already a folder called git demo. So let me just delete that in the first place and let me create this git demo again. All right, let me navigate to this particular folder. So this is the folder. Let me open up that folder using a command prompt. This is my git demo. So this would be a folder. So I would use this folder as a base folder for creating all other repositories as a part of this demo. So let me create my first repository. A repository is nothing but a folder. So let me create my first folder called first repo. And let me get into this repo. All right, as of now, this is just an empty folder. If at all I navigate to this, you would see that this folder is empty. There's nothing much in this folder at all at this moment. Okay, so let me create a repository out of this. How do I create a repository of this? It's pretty simple. I just run a git init command. When I say git init, it means it's going to initialize a repository. As of now, the folder contained nothing in it. It was an empty repository. So it initializes an empty repository in this particular folder. If at all I look at my content, you would see that there's a hidden folder. This would be a hidden folder since I've configured my Explorer to view all hidden folders. I see it, otherwise you wouldn't see it. So a folder by name .git is created within this first repo. And this was created because we ran the command git init. If I get into this folder, I see a bunch of directories and other configurations. If you see, there's something called as a hooks directory, a couple of configuration files that are here in this directory. All these relate to one or the other type of a client hook that can be enabled. And there's info, there's objects, there's references, a bunch of stuff that is there. So what is this folder? This is a magical Git folder, and this is created whenever a repository is initialized. So by default, if at all you get into any Git folder or any Git repository, you would see this .git folder. A word of caution, do not get into this folder and try to modify anything, because if you fiddle around with this and corrupt this particular folder, your whole repository will go for a toss. So let me come out of this and let me show you another thing. Now, if you notice here, when I was in the folder, the repository did not have anything after this. Now, when I say git init, there is something called as a master that shows up. So typically what happens is whenever a Git repository is created for the first time, it creates a default branch. The name of the branch is called master. And that is why you would see master within braces. This doesn't mean anything else other than we have a repository out in this particular folder. And by default, there is a branch called master, and we are currently on that branch. If at all I create multiple branches in this folder, whenever I navigate to different branches, the branch name within these brackets would change. All right, so far so good. So we created a folder, we made it a Git repository by initializing that with a git init, And then I've not put anything yet in the repository. So let me try to do that. Let me create a few files within this particular repository. So I use a touch command. Touch is a Linux command. It kind of creates this particular folder. If at all you're not comfortable with the file creation by this way, you can always use a file explorer and create some files in this. So I create a file called touchmaster.txt. I'll open up in the notepad. Okay, so this is my first file. That's what I'm going to write inside this. I save this and I come out of this. All right, now let me do a git status command. So what does this tell you? There's no commit set. You're in the master branch. There is an untracked file and this shows up in red. It also gives you all the commands that is supposed to be run. So if at all you want to add this file, you would say git add and the name of the file, and then you're going to commit it. So what happened is that when the repository was initialized, it was an empty repository. Now that a git notices that there is a new file in this repository called master.txt. If at all you want us to let git know that you want to track this file, we need to add this to the repository. So the command to add that is called git add. I can specify either the name of the file or I can give a wild character saying git add dot. Now if I run the git status command again, it says there's no commits yet. Added a file, and the file which was earlier in red now shows up in green, and it says it's a new file, master.txt. All right, it also gives you something called git remove command if at all you want to unstage or undo your changes. So what has happened is the file which was earlier untracked is been added into the git index, or it is ready for staging, or it's in a staged state. Now I can go ahead and commit this file if at all that's what I want to do. So let me do that. I'll do a git commit -m and I give a message that I want. I would say this is my first git commit. All right, I run the git status command again and see it says on the branch master, nothing to commit. It's all nice and clean. So typically what happened was I created an empty directory, made it into a git folder by doing a git init. I put a file into it. I made some changes to the file. I added that file into the repository and I committed to the repository. If at all I run the git log command, it says this was the commit ID or the commit number or the commit hashtag, and this is the author. If you notice, this is the email ID and the username that we set earlier. And this was done on this date, and this is the commit message that is there. All of it looks so good. Let me do one more commit into this repository. So I will touch master1.txt. I'll put in another file. I'll open up this particular file. Write something into this. All right, I save this change. Let me also open up the older file, make some more change into this. All right, so what I did, I modified the older file that existed. I also added a new file to my repository. Now, if I run the git status command, it says modified this file, which is showing in red, and it says you have one more file, which was an untracked file. All right, now let me add both these files because these are the changes that I want to incorporate. I would say git add dot. I run the git status command again, and it says now this is a modified file. This is a new file. Looks good to me. Let me go ahead and commit this. So git commit with a message that says this is my second commit. All right. If I do a git log now, it shows both the commits. The first commit is the one that shows up at the bottom, and the topmost one is the latest commit that is there. So far, so good. If at all you notice, I'm doing all these git commands without really connecting it to any git server. I don't need any network connection for doing any of these things. I can keep on doing more and more git commands and run git commands the way I want to without really having any connections to the git server. Now that I have my changes the way I wanted, and I've checked in all the code changes into my local repository, I may want to share my repository with somebody else and work in a collaborative way. So the way to do that is, as I mentioned earlier, to host this repository or to push this repository onto a Git server. I already have a GitHub account wherein I've registered myself using my username and password. So I log into my GitHub account using my username and credentials, and let me go ahead and create a new repository. My repository is already there on the local system, so what I essentially need is just a placeholder for my repository so that I can link them together and push the content from my local repository to the server. If you notice, the name of my repository is this first repo. So let me copy this. I would create a folder structure or a repository structure on the server with the same name so that when I pushed my repository from my local box, it will go ahead and get created in the server. So the repository name should be the same as what I created on my local box. Description, I would say this is my first GitHub repository on the server. This is just an optional description that will show up. And if you notice, I can't have any private repositories. So whatever repositories that I'm going to create here would be a public repository. So I choose public, and I don't want to initialize this with a README file or anything of that because I already have a repository with some content with some code checked in. All that I need is a placeholder for my repository on the server. So with this option, with just the name and with an optional description and the repository being public, I go ahead and click on the create repository button. So if you notice, it gives me a bunch of commands that I would need to run in order to create a repository and push it onto the server. And also, important point, it shows me two URLs. One is the HTTPS URL and the other one is the SSH URL. As of now, we do not have any SSH keys that is set up. So let me use this HTTPS URL to connect my local repository with the repository on the server. So I've done all these things. I already have the repository set up. All that I need is a placeholder for me to connect my local repository with the server URL. So this would be the command that I need to copy, which essentially links or adds an origin with the URL of the Git server. I just copy this command and run it here. Git remote add. The name of the remote is called origin, and it points to an HTTPS URL, which is nothing but the placeholder that I've created on the server. All right, so let me check if it's added correctly. Okay, the URL looks good. I'm all set. I've got 2 commits in my repository. I'm done with all the changes. So let me try to push my repository onto the server. The command for doing it for the first time is git push -u. This is for linking the upstream origin master. So git push -u upstream linking origin master, link the master branch of my local repository with the master branch on the server repository. And where is it going to push? It is going to push by default to an origin, and the origin points to this URL. All right, let me try doing this. So it essentially opens up an URL asking me the credentials with which I need to log into my GitHub server. So let me just copy and paste the username and the password with which I have registered. I would say login. Okay, success. So I'm able to create a repository on the server, and the content seems to be pushed, and it created a new branch called master. It has linked the master branch from the local repository with the master branch on the server. So let me go back to my server and refresh this page and see if all my commits have come in. master1.txt. If at all I see the commits, there seem to be 2 commits. This is my first commit, this is my second commit. And if at all you notice, each of this commit comes with a hash key or a hash ID, which contains the details of my commits. In this commit, the files were added. This was the line that was added. If you look at the second commit, I added these lines I made this, one line chain that was there. I also added this new file which was not existing. These are the two commits that existed. And if you see the timestamp of the commit, this is the commit which was committed 15 minutes ago. So what does this mean is that the commit is the timestamp when we actually committed the code in the client. The pushing is just after we have committed the change, we have pushed it. So there's no timestamp of the push that happened. This completes the first part of the tutorial wherein I create a repository on the client and then I pushed it to the server after creating a repository skeleton on the server. Now let me demonstrate to you the SSH configuration that is required for creating a pair of SSH keys and ensuring that I connect to the GitHub server using the SSH mechanism. So for doing that, I need to first create a pair of private and public key. The command to do that is SSH keygen -t. I will use the RSA mechanism for creating my keys, capital C, and I need to specify the email ID using which I'm going to connect to, or I need to create the keys for. Alright, so generating a private and public key pair, it says, let me know what folder should I create the keys in. So by default, the keys are created in the user home directory under a .ssh folder. So this is pretty good for me. So let me go ahead and say that, that's fine. Enter a passphrase. So let me enter some passphrase. Keep in mind that I would need to remember my passphrase because when I'm going to authenticate myself using SSH mechanism, it will challenge me for this particular passphrase. I need to enter the right passphrase so that I get authenticated. So the key is generated and by default it is created in this particular folder. So let me go over to that particular folder. And this is the folder where the keys is generated. You would see a public key and a private key that is created. Let me open up the public key with a notepad and then copy the contents of the whole file. And now I would need to stick it in on the server so that I can get myself authenticated using SSH keys. So I've logged in to GitHub using my credentials and go to my settings. And you would see an SSH and GPG keys. Let me click on that. As of now, there are no SSH key or GPG keys. So I will click on new SSH key and let me paste my public key that I've copied. And I would say add SSH key. It prompts me for my password just to make sure that I've got the right kind of authentication to be adding a new key. So this one looks good. That means the keys were added successfully. Let me check if my SSH keys are working well. So I do SSH -T. I would say git at github.com. This is just to double check if my SSH keys are authenticated correctly. Are you sure you want a connection? Yes. You want to continue? Yes. All right. Now a check for my passphrase. Let me enter